Hi, everyone, and welcome to one of this year's faculty roundtable discussions. I am excited to join you and act as your host for today's event, but you won't hear a lot from me. The whole point is to get to know the faculty, and today's faculty are here from the Daniel J. Epstein Department of Industrial and Systems Engineering. And without further ado, I'm going to have them introduce themselves. And then after they introduce themselves, I'm going to tell you how this whole thing is going to go. But why don't you kick us off, Dr. Palmer?
Hi, my name's Kurt Palmer. I'm one of the faculty members in Industrial and Systems Engineering, and I teach our courses in data analysis and simulation.
Dr. Kasha?
Hi, my name is Yalda Kasha. I'm a faculty at the IAC department. I mostly teach human factors and engineering management courses and statistics.
And Dr. Suen?
Hi, folks. I'm Sze-Chuan Suen. I'm an assistant professor in the department. I teach an introduction to probability and stochastics.
All right. Well, thank you all to you for being here. I really appreciate it. And for all of our guests, welcome. Thank you for joining us. I don't know if I introduced myself. My name is Paul Ledesma. I'm the Executive Director of Undergraduate Admission, and I'm happy to be here to facilitate this conversation. Here's how today's session is going to work. I'm going to run this kind of like a talk show for about the first half of the session, where we're going to talk about the discipline, the academics, the curriculum, the courses, the research, everything to understand what industrial and systems engineering at USC is all about. And then as we kind of get through that conversation, we hear from all of our panelists, then I'm going to open it up to you all for your live questions and answers. So right now, just so you know, I've disabled the chat. I've also disabled the Q&A process because I don't want you to think about those things right now. At a certain point, I will open up the Q&A process and I'll ask you to start asking questions. So be thinking about questions you want to ask these faculty as you go. As a quick warning, this is not a session on admission. And so we're not going to handle admission questions. We have plenty of admission information sets for that, which I will direct you to. But this is all about the discipline, and these faculty are here for this one event only. So please focus your questions on our faculty and on the discipline of industrial and systems engineering. Just so you know, when we do open up the Q&A, it will be an upvote process. And so as questions are asked, you all can upvote the questions as you go. Ask as many questions as you want. We're going to start at the top with the most voted questions, and we'll work our way down to get to as many as possible. And we will end our session today at 4 o'clock. So we got the hour to get through. So without further ado, why don't we kick it off with the seemingly easiest question of all of them, but likely the hardest to answer. And I'm probably going to let Dr. Palmer kick us off with a start here, but of course, everyone is welcome to jump in. What the heck is industrial and systems engineering? And for preface and context, we have our audience is mostly high school students. Industrial and systems engineering does not exist in high school. We don't know what this is. We're thinking about engineering. It's got a weird name. It sounds like a factory builder, like, you know, so let's start there. And I know, Kurt, we've talked about this before, but Kurt, can you help us understand industrial systems engineering?
I can give it a shot, sure. Industrial and systems engineers do a huge amount of different kinds of things. Just as a few examples, we're into things like modeling the progression of diseases through populations, or allocating scarce resources like toilet paper when we're running out of it. Supply chain management, there's that toilet paper issue again. We deal with ergonomics and safety issues, like you don't want airplanes running into each other on the taxiways around airports. That makes for bad days for people. Let's see, we deal with data management. How do you store it and retrieve it and make use of it? We deal with organizations and people. We're probably the most people-aware engineering discipline. And we also deal with things like, how do you make projects move forward? How do you make sure you manage the trade-off between what people want done, how fast they want it, and what they're willing to pay for it? So that just gives a quick thumbnail of a few areas of interest within industrial and systems engineering.
Dr. Kasha, Dr. Suen, anything else you'd like to add into that from your perspectives and the work that you do?
I like to tell my students that industrial and systems engineering, it's a discipline that tells other engineers how to do their jobs, right? So in another word, we understand the systems. So you get exposed to different disciplines through industrial and systems engineering. You get to see how mechanical engineering works, how computer science works, a little bit of chemical engineering. But the point is, we understand what the systems are made of. And as Dr. Palmer mentioned, one of the most significant factors in the systems are humans that sometimes go unnoticed in other disciplines. And we look at how these subsystems, human, the machine, and other factors are working together and interacting with one another and how we can put them in the best places to get the most efficient system that works as smooth as possible. And that can apply to any industry. We are in healthcare, we are in aviation, transportation, manufacturing, oil and gas, and any industry that you can think of, and we're interested in AI, tech, we have a representative from an industrial systems engineering.
I would agree with that. That was a very good explanation. Nothing more to add here.
Okay, great. Let's dive in kind of from a slightly different perspective, but it's a similar question, and it might already have been addressed, so I apologize, but I want to take this from a different perspective. You know, we have students in the audience that are thinking about engineering just as a giant discipline, right? And they're not 100% certain. There's a lot of people that aren't really sure what they want to do. If we think back, if we can all remember back in the day to being 17 years old, and you know, I'm decent at math and science, I'm digging where this is going. I see this entire world of engineering, and I see things like computer science because maybe there's a programming class in my high school, and I hear about artificial intelligence in the world out there, and I think that's the way that I need to go now. Or I'm thinking, oh, I love planes, and I'm thinking about aerospace engineering. And Yalda, your question kind of touched on this. Why industrial systems engineering? And because I've never heard of it as a 17-year-old, right? So it's kind of the same question, but from a different perspective, if that makes any sense, Kurt.
Sure. So industrial and systems engineers, first of all, are actually engineers. So we're worried and interested in how things happen, right? You know, if you might be familiar with, you know, like television shows like How Do They Make That, right? You know, like other engineers, you know, I can sit and watch that for hours on end. All the different products and how they're manufactured and stuff like that. So that's the beginning part, but that's not all that we are, because industrial systems engineers also understand, maybe more so than a bunch of other engineers, that if you're going to get work done, you need resources. And one of those resources is money. So you have to be able to go to a business manager and explain to that person why it is that what you're thinking about doing is really going to help the business, is going to make a difference to the cost of the operations and the profitability and the competitiveness of the organization. Right? The other thing, like Yalda was mentioning a little bit ago, is that we're into people, right? Industrial engineers are very, you know, amongst engineers, extroverted. That's sort of like, you know, the extroverted engineer is the one who's looking at somebody else's shoes rather than their own shoes when they're standing up against the wall at the dance. But people used to joke around. I've had, you know, students in our classes that say, what does ISE mean? Well, it means I'm a social engineer. And they're not talking about, you know, trying to pull the wool over somebody's eyes and trick them into doing something they didn't want to do. They're talking about, I'm worried about how people fit into getting things done. Every business that I know of, whether it's, you know, NBC Universal and they're making television programs, or Taco Bell and they're making, you know, burritos, they all involve people, not just equipment. So how do you make it so that the people can coordinate well with the equipment and the materials so that everything comes together? It's like choreographing a dance. And that's where we add value, is looking at the whole dance from the top level. That's what it means to be a systems engineer, that you're worried not just about, you know, does the light switch come on when people flick the switch on the wall, or does the light come on when people flick the switch on the wall, or do the gears turn in the right way so that the vehicle goes down the street? You're worried about the whole thing and seeing how all the pieces come together. So if you're working on a project to build an aircraft, for example, you know, you've got the mechanical engineers worrying about, do the control surfaces move? You got the electrical engineers worried about, can I get power from one place in the aircraft to another place in the aircraft? And you have to have somebody worrying about, okay, so when you run the electrical lines through the aircraft, is there going to be a place for the pilot to sit? When you put the big engine in there, is it going to be so heavy that the aircraft can't take off? Are there going to be, when we're assembling it, little bits and pieces still left unattached that are floating around in the aircraft when you're trying to do barrel rolls? That's not a good idea either. So you have to have somebody who's sort of taking an overview of the whole thing and making sure that all of the details of making the thing come together so it'll work are actually being considered, that nothing is being left to chance.
I love that response. And I think that you blended into one of my next questions, which I don't need to ask now, which is basically how engineering and business come together in this degree program. Because we have a lot of students from high school that are thinking, I don't know, maybe I want to study engineering, maybe I want to study business. And this is a really nice mix of the two, because it's where engineering meets business. I like to say that ISEs engineer better businesses. And what I'm taking away from your comments right now is it's also where innovation meets reality. Like this idea of like, I got an idea, but we're going to make, this is how it's going to work, right? So that reality of design versus actual real thing, real innovation is an interesting comment. So thank you for that. I want to switch gears a little bit and now talk a little bit more about the USC concept of ISE and related to the undergraduate curriculum. And sorry to keep going back to you, Kurt, and of course, Dr. Kasha, Dr. Suen, please jump in as necessary, but I know you have a stake in this. Can you explain how the undergraduate curriculum works and maybe help us understand how that student would start in industrial systems engineering as they go through it?
Well, sure, I'd be happy to. I can outline the degree program, but I also want to answer that question about where does somebody start? Because it's real important to know that you're going to be getting industrial engineering content from the very first semester you're here with us. We have a course specifically for first semester freshmen called Intro to Industrial and Systems Engineering. It's taught by a faculty member who has both industry experience and academic experience. And the whole course is a survey of different things that industrial systems engineers end up doing, different kinds of jobs that they can go into, how they coordinate with each other, how the profession sort of lays out how we help businesses get things done, how we make sure that customers in the end get what they need. So that's the ISE 105 and Introduction to Industrial and Systems Engineering. That's one of the first courses you take in our program. But let me give you a broader overview of the entire degree program. So like every degree program at USC, we start with general education. And I don't mean you're doing general education for the first 2 semesters and that's all you're doing. No, it's sprinkled throughout the entire 8 semesters, but it's a foundational piece of a degree program. And the reason engineers take general education is because you don't do engineering in an ivory tower. You don't do it in isolation. You do it in the world. There are people that are going to have to live with the results of your decisions as an engineer. So you should understand what matters to them, and that the things that matter to one person aren't necessarily the things that matter to another. Different people around the world actually have different priorities, different values. And so you have to be aware of that to take it into consideration properly when you're making decisions that are going to affect those people's lives. So this is why general education is an important component of every degree program, but also as part of an engineering program. Then after we talk about the GE component of the degree, there's the math and science component. Engineering is applied science. We're taking physical phenomena and figuring out how to exploit them to accomplish the things that we want to do in the world. So you can't really exploit math and science if you've never studied it. So there's a math and science component to the degree program. You're going to take some physics, some chemistry, some biology, some calculus. In our program, linear algebra is an important skill in mathematics too. Then we get into the heart of the ISE program. This is what we call the core. These are the courses that everybody takes. They're the fundamentals. And we go across that broad spectrum of disciplines that I was describing earlier. So you're going to take some courses in probability modeling and data analysis. You're going to take some courses in optimization, learning about how do we go about allocating those scarce resources. You're going to take some courses in project management and work and organization, understanding how businesses function and how we manage that trade-off between what do people want, when do they want it, and how much are they willing to pay for it. You're going to take some information and management courses. How do you set up databases? How do you store and retrieve information? You're going to take courses in simulation, human factors. Let's see. Oh yeah, systems engineering. How could I forget systems engineering, right? So if you're going to build an aircraft carrier, How do you figure out what needs to be done on a daily basis when, somebody at the Pentagon says, I'd like one over there, sort of like the Enterprise, maybe a little bit of Ronald Reagan thrown in. Can you do something like that for me? And you got to figure out, from that sort of vague description at the top line, how do you work it all the way down to what are the welders doing tomorrow? Okay, so that covers the core of the discipline. We also have as part of the core our senior projects class, which is a really unique experience where we hook you up for a year with a local company that's got a problem in their business. And you and a couple of your classmates are going to work with that company to understand the nature of the problem, diagnose it, figure out what's the real cause of the problem, and then come up with a solution that you're going to try and sell. That is, get the company to agree that your solution is really going to work for them, and then go about trying to implement it. So those are all required courses. Then we also have a set of electives. Right? All the students have to take a few electives. You get your choice from a broad list of possible electives. You could be dealing with how do we measure and track the performance of systems to make sure that customers get what they want. That's called statistical quality control. Or you might be dealing with things like how do companies store information and retrieve them from different databases. So you might have a database for your customers, another database for your suppliers, another database for your employees, another database for your equipment. And you're trying to organize and manage all of that information to be able to make sure that the products and services your company delivers are going to be done in the right way. So that's called enterprise data resource planning, right? Then there are also possibilities of taking courses in a variety of tech related areas. So you can get into analytics type courses or hacking kinds of courses, ethical hacking, not black hat stuff.
Love how you
or
have to
machine learning, all those are possible electives.
This is really great. And thank you for that overview. I put a link for everyone to see in the chat so you can reference that and look at the degree classes online. But also, I'm curious from all of our faculty, what classes you have experience teaching or maybe what you're teaching now to talk about that class. Dr. Kasha? You're muted, actually. Sorry about that. I caught you when you're muted. I apologize.
So one thing I want to add, I actually graduated from the IAC department. So I was a student at the IAC department. I did my PhD. I actually had one of my classes with Dr. Palmer. She joined later in, so I never had her as a professor. But it's an opportunity to take different aspects. I've taught about 9 courses over the past 3 years, 9 different topics. So courses that I teach project management, human factor courses. We have a new course this semester for engineering management. I think it's an introduction to engineering management. We had this in a graduate level, now we have it in undergraduate. I teach statistics courses. I'm running out of names, I think, but mostly I teach it is longer. I'm just don't have the presence of mind right now. But I teach a variety of courses, and I get to work with our undergraduate students in at least 2 or 3 courses throughout their 4 years at our department. One of the courses that we have that it's fairly unique to our department. It's called it used to be called Work Technology Organization, and it's now Socio-Technical Systems, and it is geared towards our senior students, not like upper level, seniors, sometimes juniors. And it is the course where you get to practice and put together everything that you've learned through the program, not in the context of a capstone, but okay, so I've learned all these things. Now, how do they relate to one another? How can I solve a problem that a company has using the tools and techniques that we did? So that is one of the courses that students have good experiences taking.
Dr. Suen, anything you want to jump in on? I mean, obviously, I know also you're a relatively new faculty member, so I know there's some hesitation to jump in here, but anything you want to talk about with teaching and courses?
So I teach one class, and I have for the last 7 years. And so, yeah, so I teach probability and stochastic. It used to be a junior and senior level course, and this year we've changed it so that it's a sophomore and junior level course. But I think it's a fun course because it's the first class that students get to take on probability, which is one of the, more mysterious but more intriguing tools that we use in our trade. And it's fun both because you get to see new concepts for the first time, but we also take students through the course to learn things about Markov chains. And it turns out that Markov chains are one of the most fundamental tools used all over in industry, in graduate work, in systems design everywhere. And that's just taught at this very introductory level, and you can walk away with, good knowledge, and as Yalda said, then use it in various applications. And so I think it's very exciting. We get to learn that stuff very early on as an undergrad.
Could you expand and hopefully help some of our students differentiate between hearing about probability, hearing about statistics by use by an engineering department or an engineering major is one thing, but also high school students have statistics in their class. And I would tell students that's not important. You don't need that in high school. Can you talk about the difference between the statistics in high school and the work that you're doing with probability, statistics, Markov chains, anything else that differentiates that? Because I think they see like, but I see this in your curriculum. Like, yeah, but different.
No, I mean, high school statistics is important. You should learn that.
No, actually, it isn't. I have to step on that. It's not. I'm taking that out of your mouth. You don't need it. It's not important for admission. If you take that, you won't be admitted. You need calculus. Stats is something that's fun as a bonus. Sorry to step on that. But if you tell them that, they're not going to be admitted. So we do need calc. Sorry.
You need calc too. You need calc. In fact, we'll do some calc in our probability. You look at changes over time. So
there
that's
you go.
Definitely part of stochastic processes. Yeah, we look at probability and statistics as two separate topics. We start from the beginning. You don't have to have taken statistics or probability in high school. You definitely can, and it's great if you have. We expand on those topics and we try to tie it to things that you can then use, right? So looking at, here's a probability, maybe you've seen it before, but how do you use it when you're thinking about how long is it going to take someone to get through a line at Disneyland, right? So if you're consulting for Disneyland, maybe you want to know about expected amount of time that you need to wait, right? Or how many people are going to leave because they've waited too long, right? So how do you turn a probability and build something into a system? And so that's what stochastic processes is about.
That's awesome, and I apologize for stepping on your comments. I think we want students to do whatever they possibly can in high school, but I don't. We have a big population that takes stats in lieu of calculus, and that's where we get into trouble. So calculus is a preparatory element.
It's not instead of, it's in addition to.
In addition to,
right? In college, you use calculus to do your statistics. It's not just algebra based.
Which is very different than.
And C has done some really amazing research in putting use Markov decision processes in a variety of applications. Can you give me an example for the people listening?
Sure. Actually, the majority of my research involves Markov chains in some way, right? So we're doing some work so I model infectious diseases, so things like COVID, which you may have heard of, but also, things like HIV, other diseases that have been around for a long time. And we can use Markov chains and processes that look like Markov chains to model these things. And we can look at things like who should be prioritized for vaccination, right? So remember when COVID vaccines rolled out? Right, LA County said, these are the people who are eligible this month, next month we're gonna have someone else. Well, that's an optimization problem. And you need to know both the risk level, so there's probability, right, of folks of getting sick. What is the outcome, right? Are they more likely to die if they're a vulnerable population? How can we do an optimal optimization on this process on who to give vaccines to, right? But we also have similar problems for hospital operations. So my work, as you can see, is in healthcare. So hospital operations, and of course for chronic illnesses as well. When should we do screening? Are there important target groups that we need to screen for various diseases because they don't know they have a particular disease because the symptoms aren't visible, right? So all of these things you can actually model in stochastic models, which are all based on Markov chains and things that look like Markov chains.
Can you give us a quick, it might be impossible to give us a quick definition of stochastic modeling and Markov chains? Because I think we're using this term like, oh, we use this. What actually is it? if that helps people understand a little bit more.
Yeah. So essentially, stochastic processes are processes where you have random variables over time, right? So you can think of a probability over time, right? And so that's what we're really looking at, right? What is the likelihood of you getting COVID today versus tomorrow versus the day after, etc.
Got it. Thank you so much. And then you guys have already dipped your toes into the question I was going to ask next, which was, can we talk a little bit more about research? What does research look like in industrial systems engineering? What are the areas of research that faculty are going on, or what you're individually involved in, or where your interests lie? And so, Dr. Suen, thank you so much for talking about your research. Dr. Kasha, do you want to jump in?
Sure. My research is mostly in human factors, which is the study of humans in the systems. And currently we are working, so some of the work that we're doing right now, so this semester we are working on the application of digital health at home hospitals, like hospital at homes. For example, when patients are released from care from any institutions and they have to go home, they either have a caretaker or no, and they have to take care of themselves. How do they do that, and what is the application of digital health? And it has different perspectives from human factors. One would be how we use the systems. Do we train the caregiver? Do we train the healthcare providers? And the other application of that would be, how do I design this system? So for example, any interface that is a communication mode between the human and the machine, or two humans who are not physically co-located, that goes through the topic of human-computer interaction or human-computer interface design, HCI, which we do actually have a course on that in the ISC department. Another part of my research is mostly macroergonomics. So macroergonomics, Kurt was talking about, if I'm designing an aircraft and okay, what does this engine has to do with the pilot? An example of that would be the MAX 737 crashes, and they dug into it and they realized that the reason why the crash happened was the failure of a technical system. But one of the other contributing factor was that the pilots, so they put in these new engines which were heavier, so they added this new technology which brings the nose of the plane down in case to balance the plane, but they didn't tell the pilots that we do have this technology. So when the technology malfunctioned, nobody knew what they need to do, and crashes happen. So in macroergonomics, we are looking at, okay, now that we have this new technology, how is that going to impact the system as a whole? How is going to impact the human component? How is it going to impact the technical component? How is it going to impact the organizational component? And how I can design this so that my system maintains its reliability, so I do not have crashes, or improve the reliability. So if I had an accident before, how can I bounce back?
Right.
So Yalda, if I'm remembering correctly, you've also done some research on ground transportation, not just air transportation, like street level intersections between rail lines and automobiles?
That is correct. So my PhD dissertation was in rail transportation, talking about the application of industrial systems engineering in a variety of industries. Was looking at how, so again, new technology implemented on trains to prevent train-to-train collisions. But this technology is supposed to slow down the train or stop it if the train is going beyond their allowed control. But this technology is blind to the objects on the track. So if there's a person on the track, there's a car on the track, this technology doesn't see it. But because now that the technology is there, the engineer becomes over reliant and they're not paying that much attention to the track, situational awareness. Now that becomes even more important when we are designing the system for grade crossing. Grade crossing, as we have a bunch of them around campus, is where a train track has intersections with the road. And we usually have gates guard the track. Sometimes we don't, as we don't have one next at the exposition grade crossing. So our research right now that we're doing with one of our IC students is, okay, now that I want to incorporate this technology, how can I redesign it so that it takes into account the vulnerability of the system and improve it so I can have safer communications, a safer commute for people, for example, around the USC campus.
Please, I cross that intersection every night.
Any other kind of higher level areas of research, Kurt, that you wanted to highlight for the department?
Well, let's see. So transportation, healthcare, what other areas do we get? Oh, yes, computing, right? Health information records, right? We have one of the nation's leaders in trying to get computing systems that contain electronic health records between different hospitals to talk to each other, so that you don't have to be bugging your doctor to carry your x-rays over to your specialist in the other building. And that's just one example, right? And when the hospitals start sharing data, they can start, data mining for ways to treat illnesses that are going to be more effective, because in a single hospital, there may not be enough cases to actually see the impact of treating a particular disease in a certain way. But if you do that across many hospitals, you get enough data that you can start seeing what's working and what's not working, and develop recommendations for doctors to treat patients more effectively. So that, being able to get, it's amazing how many different computing systems are out there. And of course, if they're built by different companies, they don't talk to each other very well. So finding ways to help those systems talk to each other, so that you're not trading information about individual patients, but sort of overall, without you have to take into account the privacy issues when you do this. So you strip away the patient's name from the rest of the healthcare data, and then you start pulling the healthcare data together to find out what's working and what's not working. But you're not making any individual susceptible to bad actors out there who are trying to raise their insurance rates or deny them care or things like that.
So another area in the department for research, I guess, is decision analysis, which I know Ali does a lot of, but I do a little bit of. And that's looking at how people make decisions, right? And so I actually have an undergraduate researcher in my lab right now who's looking at vaccination attitudes in Kenya for HPV vaccine, and how people choose or not choose to vaccinate kids. And so that's another area in ISC that maybe people don't know about, right? So how do we think about making personal decisions? If we present information differently to different people, they're actually prone to make different decisions. It's a very interesting area of study, and so that's inside ISC as well. So actually, the student I have in my group is funded through a very unique USC undergraduate research program, which may make sense to talk about now. So, and I don't know if you're planning to talk about this later, but so the student I have now is funded through Curve, which is a program that I think like the provost pays for or something like that.
No, we do. The Viterbi School. No, that's all
okay.
us.
All right. So Viterbi pays for it.
Center for Undergraduate Research in Viterbi Engineering. It's my favorite forced acronym in the world.
Well, it's a very nice name. And we get some very excellent students through them, paired up with our labs, and they can participate in research. And so they get to work with our master's students, our PhD students, right? Get a taste of research, get to see what graduate research is like if they're interested in doing that. And of course, through this process, they work directly with the faculty members. And so this may be a valuable experience if you're looking for a letter of recommendation or something like that for, a future postgraduate opportunity.
Absolutely. Absolutely. Well, thank you for that. To our audience out there, I just want to let you know that I've opened up the Q&A feature. And so I have one more question to our faculty. And while they're answering that question, you can dive on in and start posting your questions into that. And this is going to be a democratic process. And so after you posted a question or you're seeing what all the questions are, you can upvote the questions. We will go to the most popular questions first and make our way down in the remaining time that we have. Look at Paul and Paige are just right on that. Look at Paul and Paige Melendez coming in hot with the first question. Really appreciate that. we'll let that sit for a little while as people start upvoting, but it is up to you as the audience to upvote questions as they're coming in. So throw in the types of questions you want to know about, you want to learn about, and we will get back to that in a second. So my last question that I'm going to ask all of you is about outcomes. In your experience, where have your previous students gone? What types of companies are hiring industrial systems engineers? What are they doing in those jobs? Can we talk a little bit more about that process?
Okay, so I can certainly talk about the kinds of companies that have been hiring our graduates. That's something that I track fairly closely. Each spring, as our students are graduating, I conduct a survey with them to ask, what's next for you? And over the past couple of years, I've had responses from over 100 of our graduates. And, like we were saying at the very beginning, ISEs get employed in every sector of the economy you can think of. But just to give you a little bit more detail around that, there are 9 organizations over the last 2 years who have hired 2 or more of our graduates. And collectively, they account for about 1/3 of our graduates. And those companies are the major management consulting companies within the country, like Pricewaterhouse and Deloitte and Ernst & Young. The US Navy, we've had 5 Navy officers graduate from our department in the past 2 years. Companies you may have heard of like Amazon, UPS, Microsoft, Northrop Grumman are all hiring industrial and systems engineers. You might not pick up on why Microsoft would want us, because we're not writing software for them. We're helping manage their supply chains to make sure that those Surface laptops get where they're supposed to go and the Xboxes get where they're supposed to go. So we're on the hardware side at Microsoft. But those big companies only account for about 1/3 of our graduates. The other 2/3 have been hired by a host of individual one company, one graduate connections. And those cover financial management, BlackRock and First Republic Bank. They cover government operations, the city of Charlotte. Let's see, what other good ones have we got in here? Union Pacific Railroad, Chevron, Boeing, Apple, Coca-Cola, NASA, a little company called SpaceX. Right, you start to get the idea that we go everywhere. I think I mentioned NBC Universal earlier. That's one of our older graduates who's worked his way up in the company a little bit now. He'd spent time in Europe for a while, was helping to organize all of their television production in the continent of Europe. And then he's come back to the United States last spring. So now he's starting to do more work domestically. Let's see, other companies on my list here. Cathay Pacific Airways, Schwab, Goldman Sachs. Let's see, I'm trying to pick out the ones that you would have heard of as opposed to the ones that, who are they? Well, in terms of what kinds of things are we doing here, my colleagues can help join in on this, the kinds of activities you can do for a company. We've had people go to Target, for example, and they're working on managing the inventories in the stores at the different retail outlets around the country. We've had people go to work for different food production companies like Nestle, or I mentioned Coca-Cola, right? They're interested in the quality control. Are we making sure that the production lines are sanitized nightly and that they're running at the right temperature so the bacteria aren't going to grow, that nobody's going to get sick from the food that's being produced by those companies, right? Procter & Gamble has hired some of our people. So, they make a variety of consumer products like, Crest toothpaste, for example. So, how do you make sure that, the stuff in the tube is going to be what it says, and it's going to be the right amount of stuff in the tube, that you're not, overpaying for a tube that didn't get filled enough. The aerospace sector, I mentioned Boeing, Raytheon, so they're interested in both military aircraft production and commercial aircraft production. So you could be working on an F-16 if you're working for, on the military side for one of those companies, or you could be working on a 737 or a 747. And the production lines there, it's a lot of work trying to make sure that all the stuff that's coming in from the suppliers gets to where it needs to be on the production line at the right moment, and then gets installed into the aircraft properly. And then, we move on and we do the same thing with the next aircraft, and we move on and we do the same thing with the next aircraft. And, those are just, the manufacturing side. I think I had mentioned early on, if I haven't, I should, the majority of our students go to work in service sector. So that's where the company you're working for is doing something for somebody that they're either incapable of doing for themselves because they don't have the skills, or they would rather not do it themselves. They'd rather focus on something else. So this is, where you're getting involved in, the financial services, the accounting, the management services, maintenance kind of services, all kinds of different service professions.
This is great. Thank you so much. We want to get into the questions that people have asked. And as a reminder, we only got 3 questions that have gotten more than 1 vote. And so you want to get in there and dig through those questions. And if you like the question that you want to push to the top, please keep upvoting as you go. Otherwise, we're just going to start hitting the ones, and that may not be the most interesting one to everybody in the audience. So this is up to you. The rest of the session is up to you and run by you. So first question is from Eric Kim, who says, I love the phrasing of this. What does a realistic day in the life look like for ISE? As if everything we've been talking about is not realistic. He wants to know, like, what's the real deal? And I based on the phrasing of his question, I'm not exactly certain if he means from an ISE student or from a professional. And I will also phrase this, Eric, real quick. There's not an answer to this question because everybody has a different day for a different time period and different things. But who wants to take a jab at this one?
I did work as an industrial systems engineering for a while before I started my graduate studies. And as Paul said, I can't say that this is what would look like for everybody. I was a consultant. So I was a consultant, and my day would typically look like either we would meet at the office and go to the site, or we would meet at the site. And we would spend some time with people who are working there. So for example, it could be automobile manufacturing, it could be a construction firm, and typically in manufacturing area. And we would spend some time with them and ask them questions and observe. I remember just going there and standing there and just observing how people are doing the job, like what is the layout, how they are working. We would collect information, we would collect the data, and then would reconvene together as a team, because we usually work as a team. And we would just go through all the information that we received and try to categorize them. And we would do that like 4 or 5 days out of the week. And then one day we would sit down, just a couple of days, go together. So the way that consulting work is, they come to you because they have an issue, but they usually don't know what the root cause of that problem is. And it's on you to find the true problem and the root cause, because what they see is the symptom. It's like somebody goes to the doctor and they are coughing, and that's why they're going to the doctor, and the doctor realizes, okay, for example, you have a respiratory disease, or it's just something else, and then gives them medication and prescription. So that's exactly what we're doing. We find the problem, we try to see if we can recommend solutions, and then help them implement it. So that's what my daily life looked like as an engineering consultant, industrial systems engineering consultant. But that's going to be different for everybody.
I think I'll add to that, just because I was speaking to one of your alums a couple of weeks ago and talking about that same exact process and going in and making a decision. And she was speaking to some younger new employees that were coming in. And one of their biggest concerns as engineers was, what if I make a wrong decision? And her advice, which really struck me, and I really love this philosophy, which I think is more of an industrial and systems engineering philosophy, which is that there are no wrong decisions. It's just, we're going to make a decision today, and then we're going to see how it goes. And then tomorrow we're going to make another decision. And that could be in line with the previous one, or it didn't work, so we're going to go in a completely different direction. So it's understanding how to kind of tack as we go through this process, and realizing that you got plans, you got models, you got ideas, you've got data leading into this element, but then we've got human factors, human decisions and processes that we're going to throw into this and see how it works. And then also, that's never going to hold. We're going to see how this is going to adjust as we go. So it's never one exact thing. And I think that's something that's really hard for a high school student to realize, is that you don't always have all the data to make correct decisions. Engineering is not math. There aren't right answers. Here's what we think, and that sounds like I'm simplifying it, but what is the best possible answer given the constraint of the resources and the numbers and the data that you have at that time? Next question, and this is a fascinating question. It's the first one that popped up. This is, how will AI affect the ISE job market in general and ISE jobs in particular? And I'll add to that, this is the second time I've been asked this question today, but it was not about ISE. Oddly enough, it was about computer science. Why should the question I got asked earlier today was, why should someone go into computer science when AI is going to take all those jobs? And I'm like, I think we have a false understanding of what AI can do. So let's go into, I think there's a fear right now of parents, which is AI is going to change the world and jobs are obsolete. Can we talk about ISE?
So I think as an computer scientist or an industrial engineer, right, AI is something that you make.
Yeah, you make it.
Yeah, it's like AI doesn't come from a vacuum. Somebody's got to design these. And so who designs them? It's us. We design these. So these are algorithms. There are folks in our faculty who design large-scale optimization problems. That's AI. That use AI, like I do and other folks in the department, to solve problems, right? So on both sides of this, we both make AI and also use AI. And so I think the rise of AI through industry and applications in the world is just going to make it better for us, and that we have more to do, more to design, and more to use.
Another thing I would like to add is, there are two things. One is, for a foreseeable future, we will have humans in the system that have, because something that the computers can't do is improvisation. They can do what you tell them to do, but they cannot think on their own, at least just yet. So you would still have human and other components in the system that require design. Another thing is, we've gone through that like we have quality revolution, we had the industrial revolution, we had all, like, it has happened in the past that a new technology comes in and it just changes the way that we do work. It doesn't diminish work altogether. It just changes the way that we do work. And artificial intelligence is a tool that we are going to use. So for example, I know one of the research that one of our faculty is doing is to see how AI can be part of a team. It's not that I'm going to use it, it's not that it's going to replace a member of the team. It's not that, okay, now I have this new member that we call ChatGPT, but how can I work with them? And it's not that they're going to replace my job, but it's going to be another addition to the team or to a family. So it's going to change the way that we work, definitely. But it's just going to change the nature of the job. It's not going to replace the job.
Yeah, I think it gives us the opportunity to make better decisions, because a lot of decision making is considering alternatives. And the advantage of AI is it opens up a vastly greater number of alternatives that can be considered. It's still the person that's making the decision. You're not going to turn that over to the machine, but the machine is going to help you consider more relevant information and make a better balanced decision.
Thank you for that. I think there's some sort of article that was written in the last 2 weeks that everybody's reading right now. So everyone's scared because these are things that are coming up, and they tend to come up from some source. So thank you for that. Eric's got another question coming in hot with the second question of the day. Is it plausible to complete a double major in IC and another engineering major? I'll take this as a quick answer, and then anyone else wants to jump in. Anything's plausible, Eric. I wouldn't say it's very probable. You can do whatever you want, and we will gladly accept tuition checks from you for as long as you want to be enrolled to do that type of work. But you probably don't want to do that. And I would argue that 2 undergraduate degrees in engineering don't necessarily equal more value in the long run. And the ideas of competing 2, usually, I'll just read between the lines here. Sometimes students do that because they can't decide what they want to do. So they think, double major. And that's not a way to go about it. That this idea, choose the thing that sounds coolest to you. If it's ISE, great. And if you ever want to do additional work beyond that, I think what you've heard a lot about here is that ISE goes in a lot of different directions. And students often do master's degrees in different areas. And so if you have another passion of where you want to take this, sometimes that's a master's degree. And oftentimes that's the same amount of time to get a bachelor's and a master's that it would be to get 2 bachelor's degrees. And I would argue that a bachelor's plus a master's does have a little more value. So plausible, I wouldn't say probable. You can if you want, but most people don't do that. From high school, I get that question from high school students all the time, and I don't know of a student that's actually done that. It's not saying it hasn't happened. I just don't know of it. Anything else you guys want to jump in on with that?
Yeah, I'm aware that there are a few current ISE students that are attempting a double major, and they usually don't double major in another engineering discipline.
Thank
They
you.
double major in a program outside the School of Engineering, like economics, for example, or like a foreign language, for example. And this is extremely rare. And we currently have approaching about maybe 175 undergraduates in our department. And I think there are maybe 4 of them that are working on double majors.
Right.
So it is an exceedingly rare thing to try to do.
Yeah, I mean, the undergraduate degree in engineering, regardless of discipline, is a 4-year program in and of itself, a full 4-year program. And so the ideas of pursuing additional programs, we want you to do if you want to do it. Most of the time that takes place, it ends up becoming a minor. Students doing a minor or something else. And to Dr. Palmer's point, usually it's something that you're passionate about, that you want to kind of put alongside your engineering degree because it's something that you like that's entirely different. I don't worry about adding more to it because engineering on its own already has the highest value on its own, just as a single degree. So don't worry too much about that. Let's move into the next question here, which is from Max. Thank you for your question, Max. How much lab experience is available to ISE students?
Every ISE has to go through the basic math and science portion of the degree. So there's going to be chemistry lab, there's going to be physics lab, there's going to be biology lab. But within the major, we also have some laboratory experiences. Some of those are elective, some of those are within the required courses. The required courses have laboratories related to human factors. The electives have lab experiences related to manufacturing processes. We make use of the school's makerspace for that course. So there's a variety of opportunities out there. A lot of computing. We do a lot of computing within industrial and systems engineering. So we make good use of the virtual computing laboratory facilities that the School of Engineering offers. The students in my simulation class do all the time.
And just as a side note, from the top down, each of our degree programs are roughly about a 50-50 mix between theory and hands-on work. And so something may not necessarily be called a lab, but the idea of hands-on work. So for example, the idea of that senior design capstone course that Dr. Palmer was mentioning, which you're working with a company, you may not call that a lab experience. I do. I call that a hands-on experience where you're not necessarily focused on theoretical constructs related to the discipline, but actual application-based learning, which I think is important to understand. We got 5 minutes left, folks. So if you want a question answered, hit the upvote button on whatever those questions are. Get back in there because I think we lost track of that. So jump back in, push the questions up if you want it answered. We're probably going to get to just a few more. So the winner right now is Jacob. Jacob, thank you for your question. Would you consider ISE as the most versatile engineering degree offered at USC in terms of internships or career opportunities? What a biased question to ask this audience, Jacob. We love this answer, I'm sure.
In terms of the potential of different types of companies or organizations you can work for, absolutely yes, hands down. We work in, like I said before, every sector of the economy. The only question is, do they know about us yet? There are sectors of the economy that have been working with industrial and systems engineers for decades. Most of the manufacturing portions of the economy know we exist. There are other sectors of the economy that have been becoming aware of us over the last 10 to 15 years. Here I'm thinking about the healthcare industry predominantly. And then there are other sectors of the economy that aren't quite familiar with us just yet. And entertainment is one of these, although I have to, single out Disney as an organization that has had industrial engineering in it from the beginning. But companies like NBC Universal, our graduate who went to work for them, had to do a pretty serious sales job to get into the organization. And they value the heck out of him now, but they didn't realize what benefit he could provide when he first knocked on their door. And he had to do a lot of talking to help them realize why it was a good idea to hire an industrial and systems engineer.
Dr. Kasha, Dr. Suen, anything you want to add on that? You don't have to. Just want to make sure that you have an opportunity.
That's definitely.
The only thing
Right now I've got students that I supervise for internships. One of them is working for an accounting firm, doing data analysis for them, helping make sure that the client's data gets stored and retrieved accurately. Trying to remember some of the other ones that have done recently. I know one was working with a drink bottling company a couple of years back. Another's been working with an aerospace company. So a variety of different options out there.
I think the thing that I'll add on to this, just to make sure that we're providing the balance necessary, is every engineering degree is in demand. Students across our departments are highly successful. ISE is no exception. To Dr. Palmer's point, a lot of people haven't heard about ISE, but ISEs are everywhere. And I think that's the important thing to understand. And what I think when you're looking at majors from a high school perspective, there's no right answer here. There's no best degree program. There's not most successful one. But when you attend these types of events and you're hearing things that sound interesting to you, specifically when we've talked about optimization, we've talked about efficiency, we've talked about modeling, we've talked about predictive analysis, we've talked about data, we've talked about integration with business, we've talked about all these different things related to multiple industries, healthcare, transportation, everything in between. If all that sounds cool to you, then I would argue that you would find the best program when it relates to the things you want to do. And so when you attend this session, if this sounds cool, then maybe you should pursue it and try it out. But we have other sessions coming up. And this is how I'm going to wrap up our session now, because we're hitting the 4 o'clock mark, is that we have other academic sessions with other faculty from all of our departments coming up in the next couple of weeks. You register at the same space that you registered for this one, viterbi.admission.usc.edu/events. You can go there and check those out. And also, if you're not able to attend that particular day, we'll have a recording up a little bit later. There's not one best program, but I probably would guess that Dr. Palmer, Dr. Kasha, Dr. Suen would tell you that this is the best program for you. And a lot of people, I think, need to hear more about this. This is my favorite program. I love this program. It's exciting, it's innovative, and it blends the definitions of engineering and business and the ideas of social impact, which I really, truly appreciate it. So on that note, Dr. Palmer, Dr. Kasha, Dr. Suen, thank you so much for being here and presenting to our students. For all of our guests out there, thank you for attending this. If you have any other things you want to do, check out our events page, viterbiadmission.usc.edu/events for more information. Other than that, thank you and bye-bye. Have a good night. Bye, everybody. I'm going to close it out.